have seen in a high school course. So many of you may have taken some calculus. A lot of you have talked about functions, whether it's logarithms, trigonometric functions, exponential functions, things of this nature. So what we're going to do instead is talk about something that you have to get a little bit into mathematics to see in its full, beautiful formalism. But we can still understand a good deal of it without really requiring any background knowledge whatsoever. Mathematics, by the way, is best done with a pencil or a pen, or even better, a piece of chalk in hand. So I'll try to write down as much as I can for you. So we're talking about groups and symmetries tonight. And these are both words that have mathematical meaning. We're not going to worry about what precisely they mean just yet. So instead, let's just lay a little bit of groundwork. So typically in mathematics, we concern ourselves with the studies of mathematical objects. So these could be geometric shapes, they could be graphs of functions, they could be algebraic expressions, all of the things that you've seen in the 12 years of mathematics education that you've experienced thus far. And so this is not the only thing that we care about in mathematics. In fact, I would say it might be among the smaller things we care about. What we care about a great deal is not just the mathematical objects themselves, but the way that we can act on these mathematical objects with other things. And we see this all the time in high school mathematics. So an example of this is functions. So we have visual representations of functions that we're all familiar with. So I can draw the graph of a function. Here's an XY plane, and maybe it looks something like this. So here's the graph, y equals f of x. And what does this really tell me? It says the following. You give me an x, and I return a number called f of x. The x itself is not terribly important. What is important is the function itself and what it does to all of the x's. And that's what we see when we look at the graph of a function. Okay, so what can we do with this? Well, let's take the most basic type of mathematical object. And in my case, it's going to be a collection of 4 dots, the vertices of a square. And there's nothing too distinguishing about these vertices. They're 4 points in space. They're different from each other. But there's a lot of rich structure if I talk about how I can rearrange these 4 points. And the way that I want to rearrange them is with something called a symmetry. So a symmetry for us will be either I take these 4 points on the square and I rotate them. Could be clockwise, could be counterclockwise, but I rotate them in such a way that once the rotation has been completed, I still have the vertices of a square. The other type is a reflection. So I pick an axis in which I reflect the vertices over this axis. And as long as the result is still a square with 4 vertices, then that is also a symmetry. So let's briefly talk about how many of these things are there. So I have a nice list that I've generated here. So you can see on the left-hand side, I'm going to have the same square with the same coloring of vertices. And on the right-hand column, there's going to be a change. So when we look at the right-hand column for number 1, what is happening is we are rotating. So this is a rotation. And it's a rotation by 90 degrees. Oh my goodness, what's happened? There we go. So maybe I'll denote that by this, rotation by 90 degrees. Or you could think of it as rotation in the other direction by 270 degrees. So that might look something like this. If we keep going down, what we're getting is another kind of rotation. So in this case, I'm rotating by 180 degrees, whether clockwise or counterclockwise. So you see the blue dot moves over 2 or moves over 1 and down 1. The brown dot moves down and over 1, and so on. Each dot moves exactly 2 positions. If we keep going down, I'm just doing the same thing and adding 90 degrees each time. So this is rotation by 270 degrees if we're going clockwise. Or if you'd like, you can rotate counterclockwise 90 degrees. And then the final one, well, nothing has changed. And all this is rotation by 360 degrees, which does nothing. You're back to where you started. So if I'm just talking about rotations, there's 4. And one of them is kind of pointless. You don't do anything. But there's this other category, which is reflections. So there's 4 different ways that I can reflect the vertices of a square. And the way that we do that is by correctly identifying an axis of reflection. So in this case, you see the blue and the red dot remain unchanged, but I am flipping the brown and the green dot. Selected, so it's going to look like a reflection along this axis. So we jump this axis, 2 of our dots stay where they are, 2 of them flip. If we go to the next one, well, it looks like the top row becomes our bottom and our bottom row becomes the top. So this one is reflected along the midline. Okay. And then you can probably imagine what the other 2 reflections look like. So for the next one, it looks like the brown and the green stay the same, and the other 2 flip. So we have this axis of reflection. Oh, that's not even a line. That's going to bug me. I better make sure it's good. So there's our axis of reflection right over. And then the last axis of reflection is the vertical. So this gives us every possible way we can do this. There are 8 ways in total. So this is what we call the group of symmetries for the square. I'll talk about what group means in a moment. But what is mathematics if nothing else but turning real observed phenomenon into an abstract set of principles? So I'm going to challenge ourselves to make 4 observations about these 8 symmetries of the square. The first one is, when you start rotating, if you rotate again, or I should say if you rotate, say, 180 degrees, that's the same as rotating 90 degrees twice. And if you rotate 270 degrees, that's the same as rotating 90 degrees 3 times. And finally, if you rotate 90 degrees 4 times, that's the same as rotation around to where you started. So we can codify that with algebra. So if we let R be rotation by 90 degrees, so this is clockwise, then I can say that R squared is rotation by 180 degrees. And what do I mean by R squared? Because R is not a number, it's just a symbol. I mean applying R and then R again. So that's rotation by 180 degrees. So this is applying R twice. And we can keep going. R cubed is rotation by 270 degrees. And r to the 4 is rotation by 360 degrees, which is the same as doing nothing. So i.e. nothing. So we have this letter R, and it has the property that once I go around 4 times, I'm back to where I started. So we write the last one. R to the 4 equals 1. So the number 1 here means it's an action or a symmetry on the vertices of a square that does nothing. So those are the rotations. What about the reflections? Well, this can get a little bit more complicated. So I'll do this with a single example. If you take any 2 of these 8 symmetries and you do one and then the other, doesn't matter which 2 you pick, you will always get one of the original 8. So to show you an example of this, I have a sequence of 2 reflections. So the first is the reflection over the horizontal, this one. Okay. And then the second one is going to be the reflection over the second diagonal, which is this one. And it gives us the box on the right. And so you might think, how do I get from the very leftmost to the very rightmost with one symmetry? Well, we can do it with rotation. So going from this one all the way to this one is the same as, let's see, is it counterclockwise? It's counterclockwise in this case, as 270 degrees clockwise. So that's what we called r cubed. So again, it doesn't matter which 2 you pick. If you do one and then the other, you'll always get back to our list of the original 8. So we would say that this list is somehow closed under the operation of combining these actions. Okay, the third, and this is the one where I will challenge you for a little bit of thinking on your own because it can be a little hard to visualize, is any of the original 8, you can achieve them by successive applications of the rotation R and any one of the reflections. Any one that you choose, just pick one of those reflections. You can make any of these 8 with combinations of R and that reflection. The last and most important step is this relationship. SR is R cubed S. So I haven't told you what S is. So here S can be any of the reflections. Well, that's not how you spell reflection. REF. So any of the reflections. And so I'm going to do it with, let's pull this block up. The reflection that we get just along the horizontal. So here S is that one. Okay, so what is this saying? So on the left-hand side, we have to read these things right to left because first on the left-hand side, we apply R and then we apply S. So here we apply R first and then S. Okay, so to go from the first box in the first row to the second, that's going to be rotation by 90 degrees clockwise. And then if I take the second box and I reflect it through the horizontal, I get the last box. On the other hand, I can go on the right-hand side here, and we can apply S first, and then R cubed. And that's what the bottom row is giving us. So first we do our reflection along the horizontal to get the second box. And then we can rotate counterclockwise by 90 degrees. So there's R cubed. Okay, so this fundamental relationship between these two characters, S and R, is a way for us to mathematically encode everything that's happening here. So maybe I'll say something like, note also that S squared is 1. And so what this tells us is if you reflect and then reflect again, you're going to be back to where you started on the square. So now we have all we need to summarize everything that's going on here. So there's a nice, neat trim way that we can package this all together. So I use a little pointy bracket here, and I say that the collection of all symmetries of the square with 4 vertices is given by 2 letters, R and S, and they're subject to the following properties. The 4th power of the rotation is 1, so this just means if you go 90 degrees, 90 degrees, 90 degrees, 90 degrees, you get to 360, which is the same as doing nothing. And a reflection, which has the property that if you apply it and then it again, you get back to where you start. And then finally, the last one is this beautiful property we have up here, SR is R cubed S. So these are the symmetries that we get with the square. So the symmetries of the square. Okay, so we have a question here. Yes, so when you're fixing one of the reflections, it doesn't matter which one, but once you've selected it, that's it. That's the only one you need in order to do this. Okay, so this is some mathematical formalism that we're seeing right now. So it's, in one sense, visually describing what happens when we move these points around in space. But on the other hand, it's given by this purely algebraic construction. 2 letters, the letters satisfy certain relationships with each other. And that is a group, an example of a group. This particular one is called the dihedral group D8. So where does the 8 come from? Well, it comes from twice the number of vertices. We've got 4 vertices. 8 is 4 doubled, and that corresponds to our 4 reflections and our 4 rotations. We can do this with any regular polygon. So for example, I could take an octagon, which I'm going to have to draw freehand here. So I'm very sorry about that. And in this case, you're going to have 8 rotations and 8 reflections. And in this case, D16 is going to be still generated by two letters. So the rotation by, can't say 90 degrees anymore because that doesn't really make sense, but let's say rotation by 1/8. So how many degrees is that? 45 degrees. And it's going to satisfy almost the same relationships, except I get an r to the 7 in this final one. So here r is rotation by 45 degrees. And you can keep going. Any number of vertices you want. You can keep on doing this same construction, something that translates this very geometric property of what's going on with this shape into a purely algebraic construction. And this is the notion of a group. So the other word in the title of this talk, we can express it now. So what we're going to do is this is a common theme in mathematics where we observe something in nature or a little experiment that we're working on, or even just a little casual observation that we make on a chalkboard or on a piece of paper. And we try to see, is this true more often in more general contexts? Can we try to abstractify this into a framework that makes it true in general? And the dihedral group is an example of a group, and a group is what I will define for you. So we start off with a set. I'm going to call that set capital X. We don't have to define what a set is. Actually, that's a very complicated thing to do. All you need to think about is it could be a couple of vertices. It could be a bunch of real numbers. It could be like the x-axis or the real line. It could be a shape. It could be really anything. It could be a collection of pebbles on the beach. And what a group is a collection of functions or actions that accept pieces of your set and they spit out other pieces of your set. Okay? But they have to obey a certain number of laws. So the first thing is the action of doing nothing must be in our group. So the action of doing nothing must be in, may as well call it G. So let's let G be our group. So we call this the identity. Belongs to G. And what does the identity do when we do the identity and then something else in our group? Well, it's the same as just doing the something else. So maybe I'll say, okay, something like if G and H are both in G, then so is G times H. So if I give you two actions and you perform one and then the other, then necessarily we are insisting that the group has to contain that combination as well. Okay, 3. If G, H, and K are all in G, then if I perform H and then K and then G after that, that's the same thing as, well, essentially performing them in the same order, but you're grouping them differently. So this is known as the associativity law. And the final piece, and this is the one that we perhaps didn't quite see above, is if G is in G, the reverse action, which we call G inverse. And moreover, if you apply G and then G inverse, or vice versa, that's the same as doing nothing. Okay, so in the case of our dihedral group that we just constructed, if I rotate by 90 degrees clockwise, the inverse operation to that is rotating counterclockwise 90 degrees, or r cubed. So maybe I'll say, and we'll just shift this one down here. So e.g., in D8 above, r inverse was equal to r cubed, in fact. Okay. So this is a pretty hefty step up from what we've seen. So maybe you've not seen something like this in a previous mathematics course, but looking at something like this is one of the core features of mathematics, where you're taking the most important attributes of a thing that you're interested in, and you're reducing it down to a set of axioms, a set of rules. And the hope is that you can find other objects out there that also obey these sets of rules. And then you might be able to find truths about all of these kinds of things, all of these groups at the same time, rather than restricting your study to a particular example like the dihedral group. And this is the power of abstraction and generality. And this is, as mathematicians, typically what we're interested in trying to do. So here's an example: shuffling a deck of cards. So we have 52 cards. Okay. And what do I mean by shuffle? Well, a shuffle is an action which is simply rearranging the cards in some order. So a shuffle is simply a rearrangement. Okay. Is it a group? Or are these a group? I feel like that's not a very good English sentence. And the answer is yes. If I shuffle once and then I shuffle again, that's the same thing as performing a single shuffle. What that shuffle is, I don't know. It's actually quite complicated to figure out such a thing. But the fact is, that's the first thing that we need in order for it to be a group, is you do one of these actions and then another, and you get another action that's within that group of actions that you're trying to define. So yes, indeed, they are. So the identity is the shuffle that you get by not moving any cards. So a shuffle of doing nothing. I think he would probably be upset with a blackjack or poker dealer if they gave you a deck of cards and did nothing to it and claim that it's being shuffled. But that is technically a shuffle. We just don't do anything. And otherwise, you're just mixing up the cards in some pre-described way. In terms of, can we undo the action of a shuffle? It's hard to write down how you might perform such a thing physically, but theoretically, it's possible. If I shuffle one way, I can get back to where I started by completely reversing what I do in that shuffle. And perhaps the thing that I'll leave you with in this example is, how many are there? So maybe I'll pose that question to the audience. Does anybody know how many different ways can I shuffle a deck of 52 cards? How many rearrangements of 52 are possible? Go ahead and use the chat if you have some idea. It's okay if you don't. That's right, Amy. 52 factorial. an incomprehensibly large number. Why is it 52 factorial? Well, we take our first card. Where can I place it in the arrangement that follows? There's 52 positions. Then I take my second card. Where can I place it? Well, now there's only 51 positions. And then 50, and then 49, and then 48. And that's what this number is. 52 times 51 times 50. Now, if I was very well prepared tonight, there are amazing ways of trying to visualize how big of a number this is. But maybe I'll just say something like, it is so big that it is probable that no two random shuffles of a deck of cards on this planet in its whole history have ever been exactly the same. So this is indeed a very, very large number. Okay, and if we return to our vertices on a square, there's a way that you can shuffle those as well. The reflections and rotations are examples of shuffles, but there are other ones as well. How do we know that there are other ones? Well, with 4 vertices, using the logic that we have here, there'd be 4 factorial, which is 24 different ways of rearranging those 4 vertices. So 8 of them come from the symmetries we already understood, and then there's these 16 other ones. Okay. So we will finish with something that kind of makes use of some high school math. Let's talk about functions. So I'm going to claim the following is a group. So I'm going to let G be the invertible functions from 0, 1 to 0, 1. So this is the closed interval 0, 1. So all of the real numbers between 0 and 1 inclusive. And I'm going to take all possible functions from 0, 1 to itself. And those functions need to be invertible. And so what I mean by invertible is, if you'd like, they pass the horizontal line test. So you might have seen the expression 1 to 1 to describe such a thing. Okay, but let's draw a picture of what these things look like. So I could have this one right here. This is a perfectly good function. It's the line y equals x. That is an invertible function that's between, or that lives on 0, 1 and goes into 0, 1. We could have 1 minus x. Oh, see, I shouldn't have, I lost my confidence in drawing a straight line. So now we're back to square one. So this is f of x equals 1 minus x. Okay, I could throw in, oh, I don't know, something like f of x equals, I should use different letters, g of x equals x squared. That's another one. And you can get pretty fancy with these. They don't have to just be things that we're familiar with. Could be something like this, or something like this. Or it could be something really strange like this. These are all examples of invertible functions from 0, 1 to 0, 1. And this is a group where, when we want to combine 2 of these things together, we can do so with composition of functions. So G is a group if we interpret G times H as the composition function. G composed with H. So G composed with H, that little circle. All I mean by that is G composed with H of X is G of H of X. Okay, so for example, if G of X were something like X cubed, then G inverse of X is the cube root. Under the action of composition, G composed with G inverse will give the identity. So the identity is the function. Oh, we'll just call it f of x equals x. That's the function that when I compose it with any of the other ones, I always get the other one. And maybe just as an example, if f of x, well, I've used f, so let's go back to the original g that we have up there. G of x is x cubed, and h of x is 1 minus x, one of the other ones that we did. I can combine these two into a single thing. So g of h of x, that's the same as writing g of 1 minus x, which is 1 minus x cubed. This again is an invertible function from 0, 1 to 0, 1. Okay, so how big is this group? Well, it's infinite. It's so big that, I mean, saying that it's infinite almost doesn't even do it justice. We have kind of different categories of infinity in mathematics, and this one's a pretty gigantic one. Okay, so I think I will stop here. So these are some examples of groups that we see in mathematics, but there are so many more. So I would certainly encourage any of you, if you're interested in this subject further, go onto Wikipedia, just look up group. You'll have all of these beautiful pictures of different kinds of symmetries and many other examples that you can see of this type of behavior that exists everywhere in mathematics. So thank you very much, and I believe we can get on to the Q&A portion.
Yes, definitely. I'm just going to do a quick presentation about how to get into the mathematics program, and then we will kind of move into Q&A, but feel free to put your questions in the chat. As I just go through this, it should be relatively quick, which is nice. So this is all just about starting your journey at the University of Calgary. So how do you get to the University of Calgary and become an undergraduate student, specifically for this sample lecture in the mathematics program? So this is just a couple of things about the University of Calgary. So we were founded in 1966, which means we're not even 100 years old yet. But we do have 28,000 undergraduate students, 5 campuses, and 14 faculties. So we're quite a big university in Canada. We are Canada's entrepreneurial university as well. We've got quite a bit of money when it comes to research funding. And then these two are my favorite statistics down here in the corner. So we have a 94% after graduation employment rate, and then a 95% undergraduate retention rate. So that undergraduate retention rate means that students who come to us for their first year, 95% of the time will stay with us for their entire degree. So that's just kind of speaking to that student life satisfaction, everything that you can expect with being a University of Calgary student. So this is just a little bit about our admissions information. So general requirements, all of our programs are going to be based on 5 faculty-specific grade 12 subjects. So that's going to be your overall average that we're looking at. There are some programs that have some additional requirements. So health sciences, they have an additional supplemental application, which is just going to be a written piece. And then fine arts, dance, and music have an audition. Fine arts, visual studies will have a portfolio. So if you have any questions about those, feel free to put those in the chat and I can send over some links for you. And then all students must also demonstrate English language proficiency. So these are just some specific admission requirements for the Bachelor of Science in Mathematics program. So for this program, we're looking for English, Alberta Mathematics 30-1 or equivalent, 2 of these sciences, so biology, calculus, chemistry, or physics, and then an approved course or option. All of those would be looking at in the low 80s for an admission requirement. So we're just looking at the overall admission average of those 5 classes for that low 80s admissions average that we're looking for. So this can give you an idea of what grade 12 classes we're looking for you to have to get into the Bachelor of Science in Mathematics program. And then these are just some important dates that we have. So the 2024-2025 calendar year here, this is for our 2025 fall intake. The only date that's missing on here is our international application is going to open on August 1st. So if you're an international student with us today, your application is going to open on August 1st. For our domestic students, it's going to open on October 1st. And then these are all of the rest of the dates that you can expect to see across the next year and a bit. So it's really good to keep in mind to see it all laid out in front of you. But the big ones you're going to want to remember are March 1st is our admissions deadline. And then we also have our May 1st is the deadline for students to accept their offer. So for any students who have an offer for fall 2024, that is coming up here soon in a little bit less than a month. So if you haven't made that decision yet, definitely hop on your student center. And then these are just some ways to connect with us. So if you'd like to speak to a region-specific recruiter, that's just going to be the QR code on the left here. If you'd like to download our view book and view all of our programs, student life, and everything like that, that's just the middle QR code. And then if you'd like to get in contact with us in any way, we have all of our social medias and contact information here on the right-hand side. So we have Instagram, Facebook, Pinterest, and a podcast. All of these sample lectures in the series are going to be posted to our YouTube channel, so the Choose You Calgary YouTube channel. And then we also have that future students email just up there at the top. So if you're not sure who to reach out to, but you just want to reach out to someone, that future students email is a really great resource to reach out to first, and we'll send you where you need to go. And that's all I have for you guys today. So if you have any questions about admissions, I'm going to be kind of off camera here answering them in the chat. And then if you have any questions for Ryan about symmetries and groups, feel free to ask away.
That's a great question. The question is, in the symmetry of the square, it is not commutative. So SR is not the same as R times S. And that makes it very different from the number system that we know and love, the real numbers, where they do have this property. If I give you 2 numbers and you multiply them together, it doesn't matter which order that you do them. And so I guess the direct answer to your question is, well, we use multiplicative notation because it's kind of the one that was accepted when this subject was born. So it's basically context dependent. If you really mean number multiplication, you have to tell your reader that you're talking about numbers. But if you're talking about more complicated objects, like functions, like the last one that we looked at, then it really does matter which order you do your composing. So for us, what we looked at today, the operation was actually always composition. So you could certainly use G circle H or S circle R to describe that, the way that we combine those actions together. You're welcome. Oh, what are some interesting properties of the dihedral group? Oh, that's a fabulous question. That's a tough one. So I'd say that first and foremost, it's a group that represents a very easy to visualize phenomenon that we see in regular polygons. So in some sense, it's the second simplest way that we can encode interesting geometric movement from a relatively simple object into pure algebra. The simplest, by the way, is if you just took rotations. So you could also say that you take four things, one r squared, and r cubed. That's also a group. It's a group that lives inside the dihedral group. And such a thing is called a subgroup. So perhaps that's another answer to your question. What makes it interesting is the dihedral group has a very interesting collection of subgroups that are very much related to how particular rotations and reflections move the vertices around. And perhaps the last answer to your question is the dihedral groups are the smallest groups that we have that are non-commutative, that have this property that SR is not RS. The very first such example of such a thing is D6, which is the symmetries on a triangle. Hopefully that answers your question. Yes, Michael asks, are we able to do this with three-dimensional shapes? It has me thinking of mapping out possibilities for Rubik's Cube movement. That is 100% correct. There are symmetries on not just three-dimensional objects, but you can go as many dimensions as you'd like. And the higher your dimension and the larger the thing, doesn't matter how big your Rubik's Cube is, the group gets more and more and more and more complicated. But yeah, you can look up the group that represents specifically the Rubik's Cube. And you're very welcome.
Awesome. So I think if there's no more questions, we might end the sample lecture for tonight. So I'll do one final call. If there's anybody writing questions right now. Oh, there we go.
Are there mathematical systems that are also non-associative? Yes, they are. I think the smallest one is the Octonians. It could be the Octonians, but you'll have to double check. So if you search Octonians on Wikipedia and that's not the example, then the real example will be not far away from that one. You're very welcome.
Okay. Awesome. Thanks, Michael. So I think we're gonna call it. Thanks again, Ryan, for coming out tonight. Oh, we've got one more question.
Oh, higher level applications of group theory. Would you believe that group theory plays a very particular role within chemistry and also within the formation of crystal lattices? I unfortunately am totally untrained in the details of such applications, but we have chemistry students on campus that do learn some group theory in order to apply it to their own discipline. You're welcome.
Okay. One final call for questions, anybody? If not, I think we'll end it for the night. But again, thank you, Ryan, for coming out and giving a sample lecture on symmetries and groups for the students. I'm sure that they really enjoyed it. I know I did. I found it incredibly interesting. And if anybody has any questions about the sample lecture tonight, feel free to email events@ucalgary.ca, and I'm sure we can answer any questions that weren't answered or send them off to Ryan to get an answer for you. But thank you so much, everyone, for coming out tonight.